This is the first of 2 lessons on magnetic induction. The sheet you see before you shows all the learning objectives, so look at these carefully. We're going to go through these in 3 distinct parts. 2 of those parts will be through the tutorials. 1 will be done in class because it's easy to do that way. So for this lesson today, we are going to define the concept of magnetic flux, phi, apply it to various calculations and quantities, so there's an equation that goes with it, mechanisms in which flux can be changed, Faraday's law, and how it relates to changes in flux, the equation for EMF, which is just induced voltage, and then understanding the rules of multiple loops. So we will be covering these first 6 bullets. The second lesson, which will come in class, is more conceptual. It's called Lenz's law, and it helps us to describe the direction of current in a induced loop. The last lesson will look at what is called motive EMF and the related problems. So those 4 will be covered in the second tutorial. Alright, this lesson is going to build off some of the demonstrations we saw in class today. The topic is magnetic induction, and it looks at how we can use magnetic fields, or more specifically changing magnetic fields, to produce electric fields, voltage, and current. So one of the questions we raised in class was, does a magnetic field induce an electric field or an EMF? So if you're just talking about a static magnetic field, however large or small, Faraday and Henry found that no, indeed, you get nothing at all. Okay? However, and this is the key thing, to the key point, key concept for the entire lesson, this lesson and all the lessons to follow, is that you need a changing magnetic field. And there's lots of ways you can change the magnetic field. Now Faraday studied this comprehensively, and what he basically found is the quicker you can change the magnetic field in the presence of loops of wire, the greater the EMF you're going to get. So what we need to do is define a quantity that looks at the strength of the magnetic field and how much of it is cutting through a given area of loops of wire. And so this leads us to the concept of magnetic flux. Okay, and it's given the Greek letter phi or phi. It's a capital F in the Greek alphabet. Flux in everyday English sounds like change, when things in flux and change. However, in the physics sense, flux doesn't have anything to do with change. Flux is nothing more than a product of field intensity and area that the magnetic field intensity cuts through. So when we talk about magnetic flux, we are not necessarily talking about change. We're just talking about the product of, well, the symbol for flux is phi, the product of 2 things, B and A, and then there's a vector nature to it, so we'll put a cosine theta there. The units are fairly unusual. You can see from B and A, B is a Tesla times a meter squared. You can leave any calculation of flux in those terms, but it does have a name, and it's called a Weber. Looks like Weber if you anglicize it, but in the German pronunciation it's a Weber, and this is given a symbol WB. Okay, so before we can really look at the heart of Faraday's law, we need to understand this concept of flux, both conceptually and mathematically. So in terms of the vector nature, we see, let's say, representing a loop of wire. Right, and then the B field lines are moving from left to right. We always measure the direction of the magnetic field lines to the normal of the face of the loops of wire. So in this case, if the loops of wire are pointing to the left or right, then the normal is, if you will, coming out this way, so that the angle between them is 0 degrees. And therefore we get the maximum flux because a cosine of 0 is going to give you 1, so your flux is nothing more than a product of B, whatever the intensity of the magnetic field is, and A, the area of the wire that's within the magnetic field. Now in the second situation, we can see that the B field lines are running parallel to the face, or more specifically, they're running at 90 degrees to the normal to the face. So you can see a little 90-degree mark. So here we have 0 flux because the angle is 90 degrees, cosine of 90 being 0. So this is a very, very important fact, especially conceptually, just to keep you honest in terms of whether there's flux or not. So you can have a magnetic field, you can have loops of wire, but you don't necessarily have to have flux. The magnetic field lines have to be cutting through the loops of wire, the more direct they are, the greater the flux is. Okay, so once again, phi is B times A times cosine of the angle. So this then leads us to Faraday's law. Faraday's law basically tells us that when you have a changing flux in the presence of loop or loops of wire, you get an EMF. And that EMF is equal to a negative. We're going to put in an N here, where N is the number of loops of wire. And then the most general form of this equation is delta phi, that's an off-looking phi, over T. And this is best thought of as the rate of change of flux. The quicker you can change flux, the greater the voltage you can generate. Okay, so let's look at how you can change flux before we do some problems. Alright, so these are just three of the most common examples, but there are other ways of changing flux. You can simply change the magnitude of the B field. You can have it reduced or increased either by moving a magnet toward or away from loops, or if you have alternating current, then your B field will wax and wane from maximum to minimum to maximum in the opposite direction as a magnet spins in presence of loops of wire. You could simply just change the direction of the magnetic field. The magnitude could be constant, but if it's constantly changing direction, in other words the flux goes back and forth between this direction to this direction, then you'll have a changing flux. And less obvious is you can change the area exposed to the wire. This is most easily done by rotating it in a generator. So again, if this represented a loop of wire and we were rotating it about this axis around and around and around, then we would constantly change the amount of flux or the amount of area that is running perpendicular to the magnetic field lines. Less obvious and less common, you could expand the wire in the presence of the magnetic field, so there's simply more area to capture more field lines, or you could contract it, which would do the opposite. Alright, so let's look at some problems. Alright, so let's do some example problems here. These are fairly basic. Try to read through them first before you look at the solutions here. So we have a B field, loop of wire of a certain radius. Three things we want to know. What is the magnetic flux? What is the induced EMF? And if you're told something about the B field and the rate it was changing, then we're asking for what's the EMF. Okay, so magnetic flux. So that's phi. So that's new for us. So let's make sure we take care to go back to our notes and recognize that. So flux, by definition, is B dot. It's the dot product of B and A. It's assumed here that the angle is 90 degrees, so it'll be just B times A. The only thing it's not given is the area, but that's pretty straightforward since it's a loop. Area is going to be pi r squared, and if we plug in the numbers, and you might want to take time to do that now, you should get 0.02 meters squared. So we go back up to here, we've got 0.40 Tesla times 0.02 meters squared, and we'll get 0.008 Webers, or Tesla meters squared. Alright, so we ask what's the induced EMF. Okay, so generally the equation we're going to use when we see EMF in this situation of induction, of course, is the only one we have. Negative N delta phi all over T. So at this point, students will, well, we got phi is 0.008. We don't see any time element, so what do we do with this? And what they tend to neglect, even if we did give a time element, is that delta part, what's changing. And if you read carefully, we see that this assumed here, this is a constant field. Nothing's changing about it, so in fact, yeah, EMF is 0 here. There is no EMF. Just being in the presence of a magnetic field does not guarantee induction. You have to have something changing in terms of the flux, either B or A. So that leads us to B, which says if the B field is changing, then and at a certain rate, what is the EMF? So again, we're going to use, and since there's only one loop, we're going to ignore the N. It's phi all over T. But we haven't been given a time You don't need to because it's a rate. So we can look at phi as one of two ways. Well, it's b times a all over t is Faraday's law. But since they're giving us the rate at which the B field is changing, and if you look at Tesla per second, we see that really what we're given is the rate of change of B field. So that's one number. We don't need to break it up into two components, the B field and the time component, because it's given as one. So this is fairly straightforward. The negative simply indicates something about the direction, which we'll learn later. 0.05 Tesla per second times the area we found before, 0.02 square meters, and this gives us a simple answer of basically 0.001 volts. And again, the negative we can add to it, just indicates something about direction, but for right now it's just putting it there for consistency's sake. Alright, now we want to sketch how each of these things change with time. And the key to understanding the graphs is they're very similar to velocity in time and acceleration in time. If there's no change in velocity, you have no acceleration. If there's a steady change in velocity, then your acceleration is the slope of that line, and it's going to be flat. So we have a steady change in flux because B is changing steadily while area is staying the same. So if our initial flux was 0.008 Webers, okay, actually, yes, so we're starting up here somewhere, some arbitrary value, it's slowly decreasing, and it is assumed it's decreasing at a constant rate, then we expect a negatively sloped line that may or may not go to zero. So where does the EMF come in? Well, if you look at Faraday's law right here, right, I should say the delta sign should be there, then the rate of change of flux is nothing more than the slope of this. So the slope of this is going to be negative, but EMF is the negative of the slope, so it turns out EMF is going to be positive, so that's something to be careful about. And since the slope is constant, this is some arbitrary positive value. In fact, it's not arbitrary, it should be 0.001. Now I'm looking back at this answer, you say, well, why do we get a negative number? Well, because I was being careless. There's a negative here, but our rate of change is also negative, so I should add a negative of a negative to give us a positive. So if you caught that before I said anything, good for you. Alright, example 2 is a little bit more complicated, but it boils down to the same equations. We have 5 loops this time. We have a constant magnetic field. We have a 30-degree orientation between the loops and the normal line. And what's changing here is our radius. So the radius is going from 4 to 8 in a certain amount of time. We want to know what the average EMF is. So I put the word average in there because our area is going to change at a constant rate, but we're not going to worry about that too much. So we can use Faraday's law, E equals negative N delta phi all over T, and we have phi is not given, but we can calculate that as B times A times the cosine of the angle. Now, so B is given, the angle is given, but A isn't given, so we can do an intermediary step where A, and actually we're going to calculate delta A because it's changing, is going to be pi times R squared minus R initial squared. We plug in pi times 0.08 minus 0.02 or 0.04 squared. We're going to make sure we change this to meters. We will get an answer of 0.015 square meters. So we multiply that by cosine of the angle times B. So let's punch that out. Okay, we get that our change in flux, delta phi, equals 1.11 times 10 to the negative 3 Webers. So going back over here, we get negative, we have 5 loops, Delta phi is 1.11 times 10 to the negative 3. And the time it took to change was a half a second. Right, multiply those out, and we should get negative 0.011 volts. Alright, so a small number, negative again, doesn't mean anything right now. We'll make sense of that later. But the point here is the difficulty in any of these problems is generally determining what the flux is or the rate of change of flux. The first problem, you were given a rate of change of magnetic field, so you didn't have to incorporate a separate time unit. In this problem, you did have a separate time unit. You had to calculate the change in area. So we'll do more practice in class. If you have any questions, be sure to jot them down.